So instead of deriving differentials from the first principles, we're going to derive what's called the polynomial rule. The polynomial rule works with the idea of a function is equal to k x to the n, where k and n are numbers. We get the derivative being equal to kn, so k times n times x to the n minus 1 power. To show you this, I'll be taking the derivative of three functions from first principles. The first function I'm going to be taking the derivative of is the derivative of f of x is just equal to x. So from first principles, we start with f prime of x is equal to the limit as h tends towards 0 of f of x plus h minus f of x all over h. So our function in this situation is just going to be equal to x, so it's just going to be x plus h minus x over h. Simplifying the top, we have an x here and a minus x, so those can cancel, and that gives us the limit as h tends towards 0 of h over h, which is equal to 1. Now h obviously is not in that limit, so the derivative is just 1. Looking at our second function, which is just f of x is equal to x squared. So from first principles again, we get f prime of x is equal to the limit as h tends towards 0 of f of x plus h minus the f of x all divided by h. Then we take the limit as h tends towards 0 of, well, replacing x plus h where there's an x, so we get x plus h all squared minus x squared all divided by h. Next we expand the brackets, so we get x squared plus 2xh plus h squared minus x squared all over h. Simplifying this function, we have an x squared and a minus x squared, so we can cancel those out. We also have a factor of h here, a factor of h squared, and a factor of h down the bottom, so we can cancel out some of these h's, so that one goes, and we remove the square there, which gives our function equal to the limit as h tends towards 0 of 2x plus h, whereas the h goes towards 0, it is just going to be equal to 2x. So this one follows our rule. Our x squared has become 2x, so our rule of f of x equals x to the n becomes f prime of n x to the n minus 1, so that one holds. And for our third one, we have f of x is equal to x cubed. From first principles, we have f prime of x is equal to the limit as h tends towards 0 of f of x plus h minus f of x all over h. So inputting our function of x plus h cubed minus x cubed over h. Now x plus h cubed is equal to x plus h squared. We know that our x plus h squared was equal to x squared plus 2xh plus h squared, and then we can just multiply that by x plus h. which is going to give us x cubed 2x squared h plus xh squared plus hx squared plus 2xh squared plus h cubed, which simplifies to x cubed plus 3x squared h plus 3x h squared plus h cubed, which we can then put back into our original function. So the limit as h tends towards 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed, all of that on h. So our function now has an x cubed and a minus x cubed, so we can just cancel those. And our remaining values all have an h in it, so we can cancel those out. So that becomes just a 1, that disappears, that becomes a 1, and that becomes a 2. Rewriting this now gives us equal to the limit as h tends towards 0 of just 3x squared plus 3xh plus h squared. Now, as we take the limit of h as it tends towards 0, that becomes a 0, making this whole section disappear, and 0 squared would equal 0, so that disappears, which gives us 3x squared. And remember our rule, which is the f of x is equal to x to the n, and then the f prime of x is equal to nx to the n minus 1, and that one still follows our rule. Now, going onwards, we can look at all of the different variables that would come through, but the rule follows that for any function which has the form of k x to the n, where k is any number and n, which is any number, will give us the following rule, where its derivative is equal to the multiplication of kn, and you get x to the power of n minus 1. In the derivation, I only used that k was equal to 1. However, it does work with any other value of k.